This is going to be a partial repeat of what we've done in class recently, but we're going to talk about Ampere's law, and then we're going to extend that a little bit. We're going to do something slightly different than we did in class. So Ampere's law, once again, like Gauss's law, is super simple, right? Gauss's law, what does Gauss's law say? It says that the flux through a closed surface is equal to the electric field flux through a closed surface is equal to the charge divided by epsilon zero. Well, Ampere's law is very similar. It says the line integral of the magnetic field on a closed loop meaning can be any shape as long as it's a closed line, is equal to mu zero I enclosed. So once again, where is this really going to be valuable? Same place that Gauss's law is valuable, wherever there is symmetry that allows us to assume, that allows us to understand, is a better word, symmetry that allows us to understand that this relationship B dot dl does not change over the contour of this surface. So in the same way that E dot dA, we didn't want that to change over the contour of a surface. I'm sorry, when I said surface, contour of a line here. So, for example, the most common thing that we'll be looking at here, although I have another example in mind that I think will work as well. So the most common thing is we've got a wire that's carrying current. Let's say that is carrying current. Let's see. I'm going to try to do this correctly for you guys now. So as far as you guys are concerned, let's see. This is coming right towards you. All right, so let's do that. All right, so we've got current that's going right towards you, and what do we expect? Oh, I'm sorry. Let's do what do we expect first. So we expect, just from our rule of thumb, we expect that if the current is going in this direction, that with our thumb in that direction, our right-hand rule says our fingers will curl in the direction of the magnetic field. So we expect a magnetic field that will go in field lines that are circular. Please remember, the field lines that are going in this direction, that does not mean the vector is curved. At any location, the magnetic field vector is tangent to this line. So right here, this is what it looks like. Right here, it looks like this, right? Well, let's go ahead, and here's what we expect our B to look like. What does our DL look like? Well, for here, our DL is a tangent, a unit vector, or an infinitesimal increment along this line tangent to this circle. And once again, as we discussed in class, if it's not, then we just make our DL smaller and smaller and smaller until it is a straight line there, tangent to this circle. So right here, where we are evaluating this B, what is B dot dl? Well, remember B dot dl, any two vectors dotted with one another is just equal to B dl cosine theta. So where theta is equal to 0, these B and dl, that is, are lined up in the same direction, then this cosine theta will always be equal to 1, and so will always be B dl. Well, look at what happens here with the symmetry that we have. B is always tangent to the circle. dl, by definition, is tangent to the circle, so B dot dl does not change all throughout the circle. And once again, if we center this on this wire right here, and this might not look like it's centered, but it is, if we center it, then we know the magnitude of B is not going to change either. Now, how do we know that? Well, once again, just by symmetry. If there is some strength, some magnetic field strength right here at a distance r, it doesn't even matter what the relationship is with r. There is nothing that says, what if you had the same exact picture, but you didn't draw this R, and instead the piece of paper that was drawn on was just tilted a little bit, and you would draw an R, and there's nothing to distinguish this R from an R that you would draw. That's what symmetry means. There's nothing to distinguish one point from another. And so, in this respect, we have rotational symmetry. Any spot along this circle is exactly equivalent to any other spot. So that's what symmetry means. That's what B dot dl being constant means. And what that means is we can pull this B out of the integral. So what we have is the closed loop of B dot dl. I'm going to go ahead and write this out explicitly. Let's say it's equal to B0 dl. Then we're going to toss the cosine theta in here. But now we're going to take advantage of what we just talked about. We're going to say, well, this B0 does not change over this line integral. The cosine theta is equal to 1, so we can ignore it. So all we have is dl. So B0 dl equals mu 0 I enclosed. All right, so what is this? Well, line integral of this, just here, this is just r d theta. Is this dl is equal to r d theta. You'll recall that from far earlier in the course, but basically this is just the distance element in polar coordinates or cylindrical coordinates, which are equivalent here. So we have b0 r d theta. The r I'm also pulling out because it does not change over this this interval. So what do we have? This is just 2 pi r b0 equals mu 0 I enclosed. And just to make sure you can see that, so that's what we have. B0 r d theta equals 2 pi r b0, which equals mu 0 I enclosed. And then we're just going to solve that, and we come up with the magnetic field due to a current carrying wire in the plane normal to the current is B0, I don't know why I'm looking at that, U0 I enclosed over 2 pi r. And in this particular case, since I'm just going to write this as I, because I is understood here that the current in this wire is then contained here. Okay, so I think I'm actually going to stop now, but now I'm going to make another video that will then take look at a specific situation using Ampere's law to do this, to try to provide us some insight into some other problems. Okay, I will stop now. That's Ampere's law.